Hi, my name is Martin Kamme. I'm in Kennedy's 8 a.m. dynamics section.
My name is Bailey Garett, and I'm in Kennedy's 10 a.m. dynamics section.
For our extra credit project, we decided to take a couple common college objects and compare the moments of inertia and angular accelerations of each. We have a full LaCroix can, full Red Bull can, and an empty Hydro Flask.
We also will be measuring toilet paper and an apple.
To find the angular acceleration of each of our college objects, we shall use this drill, which we know is rated to 115 inch-pounds. We shall assume that torque is instant and constant, and therefore we'll be able to use sum of moments is equal to I alpha to find the angular acceleration.
We're going to be using this wooden dowel as a solid cylinder, and we're going to affix it into the drill and have it rotate about this center point with our objects attached to the end of the cylinder, and that will help us calculate the angular acceleration.
This is our highly engineered system. This is our center of rotation of our system, which is a drill with a screw inside it, drilled into this dowel from a paintbrush. And this is the center of rotation which we shall rotate all of our objects about. The first calculation that we will do is for the mass moment of inertia of the dowel. We will use the mass moment of inertia of a cylinder because the dowel must be treated as a cylinder. We will also use the parallel axis theorem because the dowel is offset half of its length from the center of rotation. We will do this calculation here once, and it will be used for every system that follows. Final value for I of the dowel is 0.00543. All the following videos are shot in slow-mo but at the same FPS, so it would be easier to eyeball the changes in angular acceleration depending on the mass moment of inertia. See if you can spot the differences. To find the mass moment of inertia of the LaCroix, we treated the LaCroix as if it were a cylinder and used I cylinder. We then used parallel axis theorem to shift the LaCroix to the center of rotation. Then we added I of the cylinder to I of the dowel to find the mass moment of inertia of the entire system. Then we used sum of moments is equal to I alpha to find the approximate angular acceleration of the entire system. To find the mass moment of inertia of the apple, we treated it as if it were a perfect sphere. And then we shifted it to the center of rotation using parallel axis theorem. And then we added the mass moment of inertia of the apple to the mass moment of inertia of the dowel to find the total mass moment of inertia of the entire system. And then we used, again, sum of moments is equal to I alpha to find the approximate angular acceleration of the entire system. Solving for the mass moment of inertia of the Red Bull can was pretty much exactly the same as solving for the mass moment of inertia of the LaCroix. However, the Red Bull is different from the LaCroix in its dimensions. It is taller, but also has a smaller radius. Because of this, we expected a different I and therefore different angular acceleration of the Red Bull. And as we can see here, the I of the entire system is smaller, and therefore the angular acceleration of the system will be bigger than that of the LaCroix. The next object that we tested was a roll of toilet paper. We treated the roll of toilet paper as a hollow cylinder, and because of its very low mass, we expected that it would have a relatively high angular acceleration because of its low mass moment of inertia. Remember the mass moment of inertia of the toilet paper so that we can compare it to the next object, the hydro flask. The final object that we tested was an empty hydro flask, which we treated as an empty cylinder. We expected that because of its large mass and relatively longer dimensions compared to the toilet paper, it would have a larger mass moment of inertia and therefore a lower angular acceleration than the toilet paper. As the video shows and our calculations show, our predictions were correct. Obviously the videos aren't perfect. Some sources of error are that I was unable to keep the drill completely stable during the rotation of all the objects, and that the trigger was very sensitive, so it was very difficult to deliver the exact same RPM for each of the objects. But we hope that we made it obvious enough that the angular acceleration changes if you change the mass moment of inertia of your system. We hope that you've learned something from watching this video. Thank you.